Our next speaker is Professor Chung Pang Mok from Shanghai Institute for Mathematics and Interdisciplinary Sciences. And he's going to talk about exponential sums and curves over finite fields, the asymptotic theory, for the next hour. Please welcome.
Thanks for coming. It's certainly a great pleasure to present some of my recent work on this occasion. So this is a joint work with my student, Xiaoyu Wang. And so his outline at the top. And let us first to discuss some notations, which we use throughout the talk. So Q is a prime power, and P for the characteristic. FQ the finite field of kinetic Q. FQ cross is the multiplicative group FQ, and we fix a algebraic closure FQ bar of FQ. Trace, right? Trace. Okay, right. So the trace of FQ to FP. And X usually stands for a smooth projective curve of FQ. And throughout, okay, you always assume it's geometrically irreducible of FQ. So X of FQ is a set of FQ rational points of X. G of X is the genus of X. FQ of X is the function field of X over FQ. Okay, right? So, and occasionally I will also use this FQ bar of X. So it's the function field of X over FQ bar. Now, let's some preparations. So as we have said, okay, so X will generally denote the smooth projective curve over FQ that is geometrically irreducible. So and little f be in the non-constant element in the function field of X over FQ. Okay. So for any positive integer n, let us define the sequence of exponential sums corresponding to this pair X and F, right? So denoted as S of n xf, defined as follows. Okay, so sum exponential 2 pi I over p trace of f q to the n over fp. Q to the n is of course a unique degree extension of fq inside fq bar, right? A trace of the element f of p. Okay, here p ranges over the set of fq to n rational points of X that do not belong to the polar locus of F. Okay, so mainly the value of F at such point P not being infinite. Okay, so this set is denoted as X prime of FQ. Okay, right, sum over this. Okay, so in particular when n is 1, so this exponential sum is denoted simply as Sxf. Okay, now so why are we interested in studying these exponential sums on curves over finite fields? So now, well, the first point is that there's a close connection between these sums and the arithmetic of curves over finite fields. So for instance, right, so remember there's a function f, right, in the linear element in the function field f x over fq. Okay, so in the case when f is non-degenerate, okay, which we're going to define below, so we have this so-called Artin triad covering y of x. Okay, so y itself is a projective smooth curve over fq that is also geometrically irreducible. Okay, so this covering is a finite Galois covering, and it could be defined by this affine equation: y to the p minus y equal to f. Okay, and in the case when the order of poles of f's are all relative prime to p, one has following identity. So namely that the number of fq rational points of y minus the number of fq rational points of x is equal to the sum of these exponential sums for the pairs x and lambda f. Here lambda ranges over the non-zero elements of fp. Okay. Now, so as an example, let us consider a case when x is p1, the projective line over fp. So just take q to p to be equal to p, and x is the usual affine coordinate function of p1. And take our rational function f to be the element ax plus b over x, okay, where a, b are non-zero elements in the finite field fp. Then in this case, the exponential sum for the pair xf is the well-known classical Klustermann sum, right? So mainly this well-known expression. Okay. And so, of course, the big question is how to estimate these exponential sums. Now, the base method is to use Artin-Schreier coverings to reduce the estimates of these sums to Riemann hypotheses for curves over finite fields, and which you know was proved by Weil himself. Now, in order to explain that a bit, okay, so we define the L function for a sequence of exponential sums with respect to the pair xf as follows. So here, because we are just working in the function field setting, so these are much simpler object compared to the previous talk. Okay, so anyway, t is just a formal variable. So the L function of the pair xf with the formal variable t, right, defined as exponential sigma over n, right, and then these are Sn x of f, t to the n over n. Okay. Now let's assume that f is non-degenerate. Okay, so that simply means that f is not neither of the form g to the p minus g for any element g in the function field of x over f to phi. This is in fact the equivalent to the condition that the Artin-Schreier covering y of x defined by this affine equation that I've shown you before is absolutely irreducible. Okay. Yeah. So now recall that we have the more familiar zeta function for the curves x, right? So zeta function of x again with the formal variable t defined by this familiar formula exponential of sigma over n, the number of actual and rational point of x times to the n over n. Okay? And of course, similarly for the curve y, right? Y being the, as I said, the Artin-Schreier cover of x defined by the pair, defined by the f. Okay? So we have the zeta function for x and y. And it's well known that these are rational functions in the variable t. So namely that, for instance, for the zeta function of x, right? So the numerator is a certain polynomial with integer coefficients, with constant coefficient 1, with degree equal to 2 times genus of x. And the denominator is 1 minus t times 1 minus 2t. And of course, similarly for the zeta function of y. Okay? Now, the key identity is as follows. So if all the poles of our rational function f are all relative prime to p, then we have this factorization identity, namely that the zeta function of y, right, the Artin-Schreier cover of x defined by f, factors as the product of the zeta function of x times the, right, times the L function, times these L functions for the right, of the exponential sums for the pairs x and lambda f, okay, where again lambda ranges over the non-zero elements of ft. Okay, now so the consequences are follows. Recall that we all know that the zeta function of y, right, is really a rational function, right? The numerator being a polynomial, right, py of t, okay, with degree 2 times genus y. So from this factorization identity, we deduce in particular that the L function for the pair xf, right, or more precisely, the L function of the exponential sum for the pair xf, well, it's actually just a polynomial and dividing py of t, namely the numerator showing up in the zeta function of y. And hence, it's of the following form, right? It can be product I from 1 to d x of f, and then this factor 1 minus alpha I x f t. Okay, here alpha I x of f is a subset of the set of inverse roots of the py of t, okay, which are algebraic integers. Okay, so and d of xf is simply stands for the degree of this polynomial, and we'll give the explicit formula for the degree later. Okay. So in particular, we have the following identity for any positive integer n. So namely, this exponential sum Sn x of f is equal to minus sigma I from 1 to the degree, right, d of x of f, the alpha I x f to the power n. Right? Yeah. And right, so you just obtain these by using what you know from this and comparing with the definitions of these zeta and L functions. Right? The second identity, right, that you draw from these is that for number of accurate and rational points of y minus the number of accurate and rational points of x is sum Sn x lambda f, where lambda ranges over non-zero elements at p. Now, so the key point, of course, is follows, namely that by the Riemann hypothesis for curves over finite fields, namely Bayes' theorem, apply the curve y, we know that the inverse roots of py, right? Namely, the numerator and the zeta function of y are all have absolute value to 1/2. Okay, and consequently, right, we call that you know this identity, right? So namely that this exponential sum, right, has such an expression where alpha I is a subset of set of inverse roots of the p1. Okay, so we thus obtain the Wave bound for the exponential sums, right? So Sn x of f has absolute value bounded by this dx of f, which is the degree of this L function of the exponential sum, times q to the n of it. So in particular, when n is 1, right, you've got this bound. This bound was first obtained by Bombieri in 1966. So in particular, say when x is just p1 of fp, and f is this ax plus b of x, okay, ab non-zero element fp, right? Recall that in this case, the exponential sum is the classical Christmas sum, and the bound that you have here is exactly the famous bound of Christmas sums, which was originally proved by Wave. Okay, so namely that absolute value of this Christmas sum less than or equal to 2 times square root of p. Now, for us, okay, we would like remember. So previously, when we said you have this factorization identity, we make the assumption that the order of poles of f are all relative prime to p. So, but we do want to remove this condition. Okay, so in order to do that, we need to employ Link's multiplication of these exponential sums that you can I think is first defined, okay, or at least first written down explicitly by Deling in this famous paper in SJ 4.5. Okay, now, so the definition follows. In order to do that, we first need the notion known as a reduced order of pole, okay, which is an important notion in the theory of Artin-Schreier covering. Now, firstly, for any closed point x of our curve, x, and again, f is the element of function field of x of ft. We set Vx of f to be equal to the following. So it's either to define to be equal to 0 if f is regular at x, or to be equal to order pole of our function f at x otherwise. Okay, and then Vx star of f, okay, is defined to be the following. Okay, you look at all the possible multiplication of f, right, by such an expression, f minus g to the p plus g, okay, where g ranges over all the elements in the function field of x over f cubed, okay, and as g ranges over all such elements, okay, you look at the minimum of this quantity, okay, right? So this is called the reduced order pole of f at x, okay. Now the basic theory of Artin-Schreier covering is that so as before, given such a say non-degenerate element f in the function field of x over f cubed, then the Artin-Schreier covering is ramified over a point x, okay, little x, precisely when this reduced order pole of f at x is positive, in which case the ramification is actually a so-called a wild ramification. All right, okay, so now to define the Link's multiplication exponential sum, okay, so just some notation. So as before, x prime should be open subscheme of x obtained by deleting those closed points with such as the pole for which I mean the Vx of f is positive. In other words, the polar the non-polar locus. Okay, x prime is the non-polar locus f. Okay, while we define x star to be the open subscheme of x obtained by deleting the closed point x for which the reduced order of pole is positive. Okay, yeah. So it might very well happen that such x is really a pole for f, but the reduced order of pole is 0. Okay, right. So in any case, so x star by definition, x star certainly contains x prime. While if the order of poles of f already prime to p, then they are actually equal. Okay, yeah. So now, so the Link then define this multiplied exponential sum as follows. So again, n a positive integer, then Sn star xf is well, okay, again you sum right over, but now sum over the f cubed to the n rational point of x star. Okay, namely for these p for which the reduced order pole at p is 0. Okay, now at such a point p, right, because the reduced order pole is 0, so by definition it can always be written in such a form. Okay, f can be written as f of p plus g to the p minus g, where f sub p is regular at the point p, while g is just just an element in the function field of x over fq. Okay, so then define this modified sum as follows: sigma over such p exponential 2 pi over p trace f to the n of fp, and then the value f sub p and p. Okay, now of course this f sub p and p, right? So the choice for these are not unique, but it's not hard to see that this expression is well defined, independent choice of f sub p and p. Okay, so in particular, where n is 1, we denote this as s star x of n. Okay, and just as before, we define the corresponding L function. Okay, for these modified exponential sum this way. Okay, L star t x of f is exponential of sigma over n Sn star except t to the n over n. Okay, right. Then the key identity, namely the factorization identity and the ensuing consequences, are valid for any non-degenerate f. Okay, with the exponential sums and the L functions replaced by the corresponding star version. So, namely, as you see, the theta function y factorizes as the product of theta function x times the L functions of these modified exponential sums for the pair x lambda f. Okay, lambda ranges over non-zero lambda p. So, and in particular again, right, so the L function of these modified exponential sum factor, however, is really a polynomial of this form, and these are inverse roots. Okay, alpha i's have absolute value q square root of q. Okay, and again, so these you have these expressions for the modified sums in terms of these inverse roots. Okay, yeah, and of course the ensuing Weibang. Okay, and also the identity relating the number of fq to n rational points of y and the number of fq then rational point of x. Okay, being the sum of these modified exponential sums for the pair x and lambda f. Lambda ranges over non-zero elements of p. Okay, and finally, so right, so the dx of f, which is the degree of this of the L function, right? So right, in fact, there's an explicit formula for that. Okay, and in fact, there is a given in terms of these reduced order of whole. Okay, and using that, you also obtain the following explicit genus formula relating the genus of y and the genus of x. Okay. Now, just for our purpose, we in fact need to use a generalization of these results, and due to Lachal. Okay, and essentially we need to consider more general class of Artin-Schreier covering. So now, for any additive subgroup G of our function field x over fq, we say that G is non-degenerate if no non-zero elements f of G can be written in the form G to the p minus G plus lambda, where G is element of the function field x over fq, lambda in fq. Okay. In the previous case, okay, it corresponds to the additive subgroup fp of times f. Okay, yeah. So in this particular case, this non-degeneracy condition exactly corresponds to what we have already explained before. So given such non-degenerate G, so as in Lachal, okay, one can define this so-called Artin-Schreier covering of y with respect to G, okay, so which we denote this way, which again is a smooth projective over FQ, absolutely irreducible. So the covering is Galois. The Galois group is abelian of exponent p, which is canonically isomorphic to the dual of G. Okay. So then one has then the identity that I have mentioned before extends to the more general setting. So namely, for any non-degenerate additive subgroup, finite additive subgroup G of FQ, right? So the corresponding Artin-Schreier covering with respect to G, right, has such a property. So namely, again, right, these identities that we've seen before, namely the factorization identity for the theta function of y, right, in the subproduct theta function x times the L function of these modified exponential sums for the pair x and f. F ranges over the non-zero element of G, and right, and the ensuing consequence, right, namely the number of fq and rational point of y and the number of fq and rational point of x. Okay, also then the difference of these two quantities is present sum of these modified sums. Okay, yeah, and finally the genus formula relating to genus Y, genus Q. Okay. Now, just a final remark is that of course, what we have talked about is a one-dimensional case, like exponential sum for curves over finite field. So it's well known that this analytic theory exponential sums could be studied for high-dimensional varieties, which this is a very rich subject and developed by Deligne, Katz, and Lamont, and other people. And most of these work is based on Deligne's the two results. But in any case, for us, at least for this talk, we only look at the curve situation. Now, let us introduce the so-called, exponential sum version of the so-called Ihara constant. Now, of course, we first need to recall the original Ihara constant. So the basic question is, so how many rational points can I curve over a finite field have? Okay, and of course, we know by Weber, so namely, which is a consequence of the Riemann hypothesis of curves over the finite field. So the number of FQ rational point of X has an upper bound, namely Q plus 1 plus 2 times genus of X times square root of Q. Now, very early on, so Serre noticed that one can, this is certainly not the optimum thing you can say. Okay, so by elementary argument, you could get this improvement, namely that the upper bound given by Q plus 1 plus genus of X times the floor of 2 times square root of Q. Furthermore, so let's say we fix Q, okay? Q is always fixed, okay? Yeah. And say again? Yeah. Well, of course, it depends on your situation. So yeah, I mean, yeah. So there are various settings for. So you consider certain class of curves, okay, and then you can you can improve. Okay. So there's such a bound. Okay. So if you want to get better, then so you look for some specific class of curves, and you can say more. Now, in any case, so if for us, okay, we are interested in the asymptotic theory. So namely that so Q is fixed, and we look at the case when the genus becomes large. Okay, so Ihara noticed that Weber was very weak when the genus is large compared to Q, namely the cardinality of the finite field. So the Ihara constant was defined as follows. So A sub Q. Okay, so A of Q. So lim sup as the genus tends to infinity of this quantity, namely the number of FQ rational of X divided by the genus of X. Okay, so it's an absolute constant that depends only on Q. And by Weber, right, you just use the Weber, right? Remember Q is fixed, and then G tends to infinity. So you immediately see that Weber give us this upper bound, namely the Ihara constant A of Q is less or equal to 2 times square root of Q. But this is not certainly not optimal. In fact, very soon, so Greenfeld and Badut were able to show that in fact for any Q, so the Ihara constant A of Q is less or equal to square root of Q minus 1. Remember, when Weber give you this, but in fact, 2 times square root of Q, but in fact, it's a not too difficult argument shown by Greenfeld Badut is that it's actually bounded by square root of Q minus 1. So therefore, now the interesting aspect of the subject is to ask for lower bound. And originally, Ihara already showed that when Q is a square, then you have the lower bound, namely A of Q is bigger than or equal to square root of Q minus 1. And hence, in fact, it's actually equality when combined with the Greenfeld-Badut upper bound. Okay, so Ihara already showed this result by using the mod P reduction of tau of the Shimura curve. Later, it was also shown. This result was shown by Garcia Stichinov using a different method, and we'll come to that again later. Okay, so when Q is a square, we know the exact value of Ihara constant. But when Q is not a square, then very much less is known. So in particular, we do not know the exact value. Okay, but in any case, so we have some certainly have these results concerning the lower bound. For instance, say Serre, you obtain this using the method of infinite class field tau. So namely that for any Q, has a lower bound of the form some universal constant C times log Q. And when Q is not a prime, so namely P to the n with n bigger than 1, then Basel-Dheelan Gaussian-Stirchinov, by generalizing the construction or originally in Gaussian-Stirchinov, they can show this lower bound for the Ihara constant. So namely A of Q with bigger than or equal to the harmonic mean of these two numbers. Okay, so here the P or so this is the floor and this is the C. Okay, yeah, harmonic mean of these two numbers. Okay. All right. Okay. So this is the original Ihara constant. Okay. So and in our work we define the exponential sum version of the Ihara constant follows. So again, so Q is for any prime power. So you look at the C of Q is defined to be lim sup of these pairs xf. Okay, whereas before x ranges over a smooth projective geometrically reducible curves of fq, and f ranges over non-degenerate elements in the function field x of fq. Okay, of course in the lim sup you look at the condition, the genus tends to infinity, lim sup of such quantity, so namely the absolute value of the Deligne modified sum for the pair xf, okay, divided by the d of xf, okay, which you recall is the degree of the L function for the modified sum for the pair xf. Okay, so right, because we have the wave bound, right, as I have said before, you have the you have the wave bound, right, for this modified sum. So therefore, so therefore the wave bound gives us an upper bound, namely C of Q is less than or equal to square root of Q. But one can easily obtain an upper bound better than that just by using the formula. So namely, firstly, that well, of course, we certainly have a trivial bound for these modified exponential sums. So namely, the absolute value of s star of xf in any case is less than or equal to the number of fq points of x. Okay, right. And secondly, for the degree of the L function for the pair, for the exponential sum of the pair xf, namely dx of f, right? So from the formula that I gave you previously, you have the lower bound, namely that is bigger than or equal to 2 times genus of x minus 2. Okay. So consequently, when you look at the lim sup of this quantity, it is certainly in any case less than or equal to the lim sup of this quantity, while this is at most equal to the 1/2 of the original Ihara constant A of Q. Okay? So in particular, by using the Drinker-Bardou upper bound for the Ihara constant, we see that our exponential sum version of the Ihara constant C of Q is less than or equal to 1/2 times the square root of Q minus 1. Okay, right. So therefore, you get this upper bound. While on the other hand, just as in the original Ihara constant, it's much more difficult obtain a lower bound. Okay. And in order to streamline some of the arguments, we also define a relative version of the Ihara constant with respect to Artin trial coverings as follows. So B of Q, okay, is defined as the following. So lim sup over all pairs, over all such a non-trivial Artin trial coverings Y of x over fq. Here, of course, as before, x ranges over the smooth projective curves over fq. They are geometrically reducible, and you look at the asymptotics as the genus tends to infinity. Okay, lim sup of this quantity. Okay, namely for such a pair, for such an Artin trial covering Y of x, right? You have this quantity the numerator is number of fq points of y minus the number of fq point of x, but the denominator is the genus of y minus genus of x. Okay, so this is the definition of the relative version of Ihara constant. It's not too difficult to show that it's in fact non-negative. Okay, even though it does not directly follow from the definition, because the numerator can certainly be negative, but not hard to show that. Okay, the lim sup is always non-negative. Okay, yeah. Now let us discuss our main result. Okay, let's see. Okay, yeah. The main result is follows. Okay, so firstly, so for any prime power q, we have the following inequality. So we remember we have these three constants, right? A of q is the original Ihara constant, right? C of q is our exponential sum version of the Ihara constant, right? We call the right. Okay, yeah, this is C of q, right? Which is defined in terms of these delaying moduli sum. Okay. While B of q is a relative version of the Ihara constant. Okay. Yeah. So we have this inequality between these Ihara constants, three Ihara constants. So namely, B of q is less than or equal to 2 times C of q less than or equal to A of q. Okay? And this is valid for any prime power q. And in the case when q is a square, then we have equality. And these are all equal to square root of q minus 1. Okay. And if q is not necessarily a square, okay, then we at this point we do not know the exact value of these constants, but at least we can say something. So in general, so when q is not a prime, okay, so in other words, the fq is not a prime field. So q is say p to the m. Okay, p of course a characteristic m is bigger than 1. Then we have the following. So of course you already have you know this inequality, right? So in order to have a if you want a lower bound for C of Q, you suffice to obtain lower bound for relative Ihara constant B of Q. Okay, so we have this lower bound, namely that so B of Q is less than or equal to, okay, again the harmonic mean of these two numbers. So now in particular, so this is of course positive, right? But remember this is only valid under this hypothesis, namely Q is not a prime. Okay, so if Q is a prime, then it's much more difficult to obtain good lower bound. So, but at least we can show that these are all positive. Okay, yeah. So, and in fact, when Q is 2 or 3, one can even get some explicit numerical result. Now, so this I leave as an open question. So remember, when Q is a square, we in fact, right, these are all identity. In fact, you have know the exact term, namely equal to square root Q minus 1. Okay, so in the case these are all equal. So as a open question we would like to raise is that does this equality hold for some prime power q under in case when q is square? Now, for the proofs, okay, so for the inequalities b of q, so namely the relative Ihara constant being less than or equal to the original Ihara constant, and inequality 2 times C of Q, the exponential sum version of the Ihara constant being less than or equal to A of Q. These are simply follow from the elementary inequality. Okay. Now, as for the lower bounds for these B of Q and C of Q, in the case when Q is a square, more generally not a prime. So in particular, giving the exact value of these in the case when Q is a square, one make use of the towers constructed by Garcia-Stirnov in the case when Q is a square, and more generally that of Basa-Thielen, Garcia-Stirnov for the case when Q is not a prime. Okay, so just a definition. So by a tower over FQ, we mean an infinite sequence of smooth projective absolutely reducible curves x of FQ, such as the following formula, right? So denoting by case of n the function field of xn of FQ, right? And we have the increasing sequence of the function field, okay, corresponding to the tower of the curve, okay, right, corresponding to the tower of curves. But in terms of the function field, it is the increasing sequence of the tau function field, okay, and such that each extension, the layer of each extension is finite separable, and we require that the genus of xn tends to infinity as n tends to infinity. Now, so the following, this is a basic result, okay, so namely that given any such a tower, you look at, Q, remember, all Q is always fixed, okay, so you look at these limits, okay, so the first limit, the number of FQ rational power of xn, right, divided by the degree of extension of kn over k1, okay, namely the base curve, okay, the function field phase, okay, then the limit of this quantity n tends to infinity always exists. Okay, it's a simple argument that it always exists, but the limit may very well be 0. Okay, but it's always finite. Okay, and similarly, if you look at the genus of xn divided by the degree of extension kn over k1, then the limit of this as n tends to infinity always exists. Okay, it's always positive, but it may very well be infinite. So consequently, if you look at the limit of the quantity, number of FQ rational power of xn divided by genus of xn, okay, so this limit always exists, and refer this as the limit of the tau, okay. So the limit, well, okay, as I said, it always exists, but may very well be 0, okay. Of course, in any case, it has to be less than or equal to the original Ihara constant A of k. Okay. So we say such a tower is asymptotically bad if the limit of this tower is 0, asymptotically good if the limit of this tower is positive, and asymptotically optimal if the limit of this tower is the Ihara constant. So the tau of Gaussian-Stirnov is asymptotically optimal, okay, in the case when Q is square. While in general, when Q is not prime, then this BVGS tau is asymptotically good. So these taus are arbitrary taus, namely that for each layer, in each layer, so the covering is a arbitrary covering, and no new other asymptotically good arbitrary taus we found that give better results concerning these Ihara constants. Okay, so in any case, let us have a brief sketch of proofs. So when so I started at I have 8 minutes. Okay. So when Q is a square, okay, so the Gaussian Stirnov tau is constructed recursively. Okay, so say x0 being t1, y0 the affine coordinate function. Okay, so the affine equation for these curves are defined this way. Okay, right. So it's a recursive tau because as you see, right, so you the y1 is a new affine coordinate for x1, and then for x2 you use this y1 coordinate in order to define the function on the right hand side, okay, and similar. Okay. So in any case, a tau of Gaussian-Stirnov, okay, has this lower bound, namely that square root q minus 1. Hence, actually, you plot by Stringfeld reduce the upper bound. Okay. While for the BVGS tau, as we already seen, okay, it has this lower bound. Okay. Now, given these towers, we then obtain the corresponding lower bound for the relative Ihara constant dq in the case when q is a square, more general case when q is not a prime, by proving this proposition, which is valid for any tower. So, namely, for any tower xn, then the limit of this tower is also equal to the limit of this quantity on the left hand side. Right? So remember when we define the relative Ihara constant, right? So relative Ihara constant, right? So this is a lim sup of such quantities, right? So and here, so we simply take the pair, right, y and x to be the successive layers of such tower. Okay. Yeah. Okay. Yeah. So once you have this, okay, then we obtain the lower bound for the relative Ihara constant d of q by using the corresponding lower bound for the limit of these powers. As for the exponential sum version of the Ihara constant CQ, okay, we only need to establish this inequality. Q times C of Q is bigger than equal to B of Q. So this is deduced from the following general proposition. So namely any sequence of and non-trivial asymptotic couplings over Q, such that the genus of the extend tends to infinity, and such that the limit of this quantity exists, not as J, then CQ is bigger than or equal to J over Q, right? This is enough because the relative PR constant P of Q is really the supremum of all such quantities, such limit J. Okay, yeah. Now, finally, these results are for the case when Q is not prime. When Q is a prime, it's much more difficult to obtain the lower bound, and we use the existent result on infinite class field tau due to Stair and others in order to show at least that these are positive. In the case when Q is 2 or 3, so we obtain the right. Remember, I told you that in the case when Q is 2 or 3, you actually get these explicit numerical results, and these follow from the results on infinite class field towers due to Guzman and Mack. Okay. Now, finally, let us talk about this limiting distribution Frobenius angle. So in general, for a pair as before, so you have the L function, right, of the exponential sum for the pair factorized in this form. Alpha I are the inverse, so Frobenius roots. And let us define these angles theta I. Well, we send you the phase. Okay, so because epsilon value is square root of Q, right? So we need phase. And now, to be specific, let us define theta I bar XM. Okay, it's an element in 0 pi, uniquely determined by the condition that is congruent to either theta I XF or minus theta I of XF. Okay, yeah, modulo 2 pi. So essentially, this corresponds to looking only at the real part of exponential sum. So refer to these as a Frobenius angle. Okay, so they are always fixed to be in the interval 0 pi. Okay. Yeah, maybe I overrun a little bit, but try to finish. Okay, so now given a sequence of pairs XM, FM, okay, such that the genus tends to infinity, the M tends to infinity, we are interested in these sequence of probability measures. So namely that, really these are distribution of these Frobenius angles. Okay? So we would like to ask for limiting behavior of these measures as M tends to infinity. Okay? So let us first make some definition. So our sequence is said to be asymptotically exact. Well, if firstly, so for any n, this limit, okay, the limit of these, really the limit of this power exam, but you look at all the degree n extension of Q. Okay, these limits exist, and the real part, okay, right, of the modified sum divided by the degree of the L function, right, the limit exists as m tends to infinity, okay, for any n. Yeah. So by simple diagonalization argument, you can show that given starting with any sequence of pairs, you can always find a subsequence that is asymptotic. Okay. Now, so the final theorem is follows. So given an asymptotic exact sequence, right? So remember lambda n is these limits. Okay. Then you have this inequality. So sum over n, absolute value of lambda n times q, the minus n over 2 is less than or equal to 1/2. Okay. In fact, this could be regarded as a generalization of the Drinfeld-Vaduz bound for these exponential sum Ihara constants. Okay. And also, as m tends to infinity, these Fourier measures mu m, right, that I have defined before, right, these Fourier measures in fact converge weakly to the following Fourier measure mu infinity with density given by this expression. Okay, right. So, this is really a Fourier series, right? The coefficient given by lambda n. Okay. So, and now just as a close this talk, okay, as an interesting example, in the case when Q is square, remember that we have this Gaussian-Stichonoff tau, right? So using the Gaussian-Stichonoff tau, we can then construct an asymptotically exact sequence, XM, FM, such that these limits, lambda n, are all equal to square root of Q minus 1 divided by 2. Okay, so in this case, the density function of the limiting measure is then given by this explicit formula. Okay, so for instance, say when Q is say 4, okay, so it then looks like something like this. So you see that there's a strong bias, okay, for the angle towards being pi, and that means that when you translate back to the exponential sum, well, that means that at least the real part of the exponential sum has a strong bias towards being positive. Okay, yeah. So as far as you go up this how, okay, yeah. Okay. So I think this is the end of my talk. Thanks for attention.
Thank you for this beautiful talk. Any question? Okay, I have one. It's about your last slide. I mean, about the equidistribution theorem, because you have a weakly convergence. Yes. What are your test functions? I don't understand.
Continuous function.
Oh, so the classical ones.
Yeah, yeah.
Oh, okay. I was not sure about it. Thank you. Another question? I have a last one. Because when Q is a square,
Yeah.
okay, we know the value of AQ. It's the root square of Q minus 1. But when it's not a square, do we have any expectation about the value of Q? For instance, do you expect that the value of AQ is still the root square of Q minus 1? Or you expect that it's a more complicated value?
It's, no one really knows. Okay.
Okay,
so,
okay.
Just a moment. It might very well be equal to this number, but I think it's not explicitly stated as a conjecture. Yeah. So, but in any case, no one so far has been able to obtain a lower bound that is better than this one.
I see, because it's very close to Q. I mean, the root square of Q. The root,
yeah. But as I say, okay, I don't think it's raised as a conjecture, but it could be possible. Okay, but yeah.
Okay.
Yeah. Of course, when Q is not a prime, then much less. Well, remember, this is when the case when Q is not prime. Okay?
Yeah, Q. Yeah.
When Q is a prime, then the best kind of low bound they were well, as I told you in the series of results. In fact, the low bound is of the order log Q, and again, no one has been able to obtain significantly better results when the prime Q came.
Another question? If not, we can approach the speaker again.